And so today, to kind of help you a little bit in some of the coding parts of the homework, Nilesh will give a lecture and talk a little bit about PyTorch and associated things. So before Nilesh starts, any questions for me? Okay, so Nilesh, why don't you take it over?
Okay. Thank you, Indrajit. So as you said, today we'll be talking about, in general, hands-on machine learning. We'll be looking at uh, how do we want to design our machine learning experiment? Like, what are the key questions we need to first even ask ourselves before going ahead? And then we'll discuss some of the tools that are commonly used to achieve our goals, implement our solution, and also document them properly. So here, some of the key tools that we'll be discussing is going to be PyTorch, of course. That's the deep learning framework that we'll be using in the class, and which it's also the most open source and widely used machine learning framework. Uh, we'll also be actually going discussing a bit about WandB, which is a machine learning documenting tool here. And other than this, we'll look essentially into we'll look at a demo problem, which is similar to what you have in your homework as well, but it's a simpler one. And we'll look of what a life of an ML experiment looks like when we go about solving this demo problem. So yeah, let's go ahead. Uh, so a life of an ML experiment is far from just training a model. It encompasses an entire life cycle that includes problem formulation, data gathering, pre-processing, model building, training, evaluation, and a continuous iteration among each of these components. So in this notebook, it's going to be a live demo kind of a lecture. So I'll will at some places I will on the fly will write the code as well. And feel free to stop me anywhere in the during the lecture, if something is confusing or something is not clear how it happened. So yeah, and here for the demo problem here, we'll be using a subset of the CFAR10, where we want to identify images of cats from images of dogs. So we'll be dealing with a binary image classification task, and we'll see how we build a neural network and train it and visualize some of the key parametrics that we want to look at. So uh, the first, let's discuss what are the key stages in the ML experiment lifecycle. So one is you define your problem. So here, the core thing that you want to do is understand the problem that you are trying to solve and define clear objectives and metrics that will be used to assess success. So then you want to define your solution, what is the backbone of your solution going to look like. So here, the key things you want to do is you want to concretize the data representation, your model, your loss, and your optimization choice. And this stage essentially involves mapping the problem to a concrete machine learning setup. And then you go about doing implementing a solution where there are multiple steps, but of course you begin with setting up the environment, deciding which framework to use. um, you want to prepare your data in a format which is amenable to your machine learning framework, and then you want to set up the model and optimization process. Then you train your model, you evaluate, and you continuously log some of the key metrics so that you can make judgments of how your training went. And for that, we will use experiment tracking tools like WandB, as I said earlier. And then like you based on the feedback that you get, like you iterate over your experiments. So we'll be going into a detail of each of these components. Of course, like we'll be like delving a lot much deeper on the implementing part. So, but that's going to be the overview of this lecture. And let's begin by like what questions we want to ask ourselves when we go about defining a problem. So as I said, like the demo problem that we'll be using is we want to classify images of dogs versus cats. So first, there are like three, I think, main questions that we want to ask, like what is my input going to look like? And here, like in most of the machine learning that we typically do, there is some form of predictiveness, like we've given for an input, like we want to predict some output. Um, this is not always true. There are going to be some machine learning problems where you don't have an output, you like it's not predictive in nature, but that's still a small part. And so far, the things that we have seen are of this nature. So like I'm uh, just using that large class of problems to define these questions. But yeah, be aware that, okay, like right now, I have one of the questions that I have listed is what is my output? It may not always be true that you have some output to predict on, but for the large class of ML problems, it will be the case. So first question is, what is my input X? And for this demo problem, the input is going to be an image of a dog or a cat. And then like you want to ask, like, what is my output? So the output is going to be a label indicating whether the image is a cat or a dog. And how do I want to measure success? In this case, one natural choice is we measure the accuracy over some set of data points, where accuracy is defined as the percentage of correctly classified images. So for this simple example of just doing this binary classification, this choice, these answers do make sense. Um, and like they are a good enough choice. But maybe like one exercise problem that we can see is like, what if we want to build Chat GPT? Then in that case, like what is like how will you go about answering these questions? So I mean, like there is maybe like not like a clear answer to these questions, but like anyone still wants to take stab at it, and like maybe interactively we can try to answer or like at least list some of the potential choices.
So I guess first thing we need to just tokenize the input so we can, work with some numerical values as we usually do. So, and then this is not, I'm coming up with, but, like a background knowledge that basically uh, giving some tokens and predicting the next. So in that sense, if we tokenize the text data, then we can have like some numerical vectors as an input, and based on whatever window size that we want, like we can say, let's look at 16 tokens and generate or predict the next one, or look at 16,000 tokens and generate the next one. But basically, that's probably how it plays out.
So you are right in a sense, but like I think that's still like going too ahead. What I would say is like what you are describing is is the component of a solution, like how you want to go about solving that problem. But here, like we are like still at a even a more basic step, that like for this problem, that like, okay, like I am a company and to me someone gave me a problem that like I should build Chat GPT. Then like what does even my input is going to be like how do I define this problem? Like build Chat GPT is very vague problem, right? Like what is my inputs? So, I mean,
You're correct.
it-
That I understand. That's what I mentioned was just the language model, which is still far from like a conversational system and all that, because like that model just predict the next word, but then how do you answer something, how many words you're going to predict, and then you're going to stop, and all these, I guess, becomes like the more the details about the problem, and we're still far from what you just mentioned, which is how do we frame the whole thing, right?
yeah, how do you even frame, like, how do you even like concretize this like statement, build ChatGPT? So here, of course, like, what is my input? Like in the, like at least a couple of years ago, like, I mean, everything was mostly like it was a conversational chatbot, which where your input is almost all of the times like just text. So like one option could be like your input is going to be a text. It can be any generic text. But okay, these days, like it's not just text, like it could be text and images like combined. So we can uh I mean, like these are like uh yeah, these are like some of the potential options, like what is my input X can look like for this problem. But again, like this may not be the exhaustive list. Like you might want to consume like any media or any kind of thing that can be captured like in by your computer. So like it can be videos, it can be a document like in some special format. So yeah, but these are like some of the simple choices maybe that we can uh, take to answer this question. And then for about the output, in the case of ChatGPT, I guess like it's still going to be something similar as your input, because like it kind of is operating in the same domain as your input. So it like in the same, I think the same applies. Like it's either the text, or it could be a text and an image, or like any kind of multimedia. So so here I think maybe I can answer it like this. But then, like, how do I measure success? Like for this vague problem, like what is my measure of success? Like, is is it going to be something similar to accuracy that I defined earlier? That uh, I have some gold answers, and I just compare it, whatever my model predicted was exactly equal to the gold answer or not. So like accuracy is one option, but yeah, of course, like it doesn't feel right, because like uh, it's like there are in the such a general case, like there is no one definition of the gold answer. So one uh, thing that we can think of is like maybe like we generate multiple answers from our model, and rate it using an expert. So I'm just listing some of the things that we can do in this case, but yeah, I'm also realizing that I may be taking too much time in discussing this. So yeah, if there's any question, like I'll stop here. Otherwise, like maybe like we should jump into defining our solutions and how do we go about implementing it. Okay, so let's come to like how do we want to define our solution. So when in defining our solution, like I feel like these are the questions that we want to answer. And this may not be an exhaustive list. So like if you by going over this lecture, like if you feel like there is something else like we want to define, like yeah, do let me know. But so the first thing is like, how do I make a collection of such inputs and outputs? Like also known as like, how do I create my data set? So for the demo example that we saw, we can gather images of cats and dogs from various sources and manually label them. Someone has already done this for us. So like the CFAR 10 dataset exists, and we'll be just using a subset of that dataset in our case. But typically for a general ML problem, like that's where you start. Like you have defined like what your X and Y is going to look like. Now you want to collect your data. And then the question you want to ask is like, how do you represent your input X in numbers? Because as we have seen, like machine learning algorithms, like just consume numbers, like they can't consume like any other format. So in this case, we can represent an image as a 3D tensor. A tensor is just a n-dimensional array. So we'll be using tensors quite a lot in this lecture, but yeah, just know that like a tensor is just a n-dimensional array. And I say 3D tensor because like an image like is typically represented by its height and width, and there are like 3 channels for RBG. So that's how we can potentially like represent an image, and that itself like gives us a like a tensor of numbers, which is a good represent which mathematical model can consume. Then we come to how do I represent my output in numbers. So here we can represent the output as a single number. We can assign 0 for cat, 1 for dog, and we want to predict either 0 or 1. And this is like we have seen in binary classification task. And then like we come to how do I map my input to my output. So this is also known as like, what is my model? So in this case, like, of course, like there are multiple choices, any mathematical functions which takes you from a 3D tensor to a like a scalar output like works here. But as we have seen, like maybe like neural networks are one good choice. So we'll be using a simple fully connected neural network with one hidden layer. Then we come to how do I measure success in a differentiable way? Because like we want to optimize this. So this is also known as like, what is my loss function? So we have already seen in the class that binary cross entropy for binary classification tasks is a good choice. And note that like you like again like we quantify the opposite of success, that is the cost of making a mistake when we are defining the loss functions. So, and the last question is like, how do I train my model? Like I have my solution defined, like what is my training process is going to look like. So also like, what is my optimizer? So here, like we'll be using stochastic gradient descent to minimize the loss. Remember the stochastic gradient descent is just a mini batch version of gradient descent, which operates on like small samples of your data set once at a time, like at one time. So these are the choices that we are making for our solution for this problem of classifying the images of dogs from cats. I think these questions you can ask for any kind of ML problems that you go about solving, and they will like kind of set up your solution like logically that like this is what you want to do. Now let's look at like how do we go about implementing such a solution using current and most popular frameworks that exist. So we first go into setting up the environment. So here, like we'll be doing a bunch of imports. So the most of the imports are like for PyTorch, which you imported like this, import torch. And so these are the primary libraries used for building and training neural networks. So, and then like there are like sub modules in this library. The important ones are, which I have imported here, is torch.nn, which contains the building blocks for creating neural networks. And then there is nn.functional, which provides functions for that are used as building blocks in neural networks. Then another one important one is the torch.optim. This usually provides implementations of various optimization algorithms such as SGD. And then there is torch.utils.data, which simplifies it provides abstraction over your data loading process for doing training and evaluation. In this case, since we are using the CFAR10 dataset, which is a very popular dataset available inside this torch vision.dataset, so that's also something that what we are importing. So let's just run this block to have all of these libraries in our environment. And now, like another set of library that not set, but another library that we'll be using to kind of track our experiment is this WandB, which is short for weights and biases. It is pretty neat a library to like log metrics, visualize results, store them in the cloud, and like just will as we go, like we'll see like how like what all we can do with it. It's I mean, it does require you to like create an account, and then like when the first time you run it, like you have to enter some of your credentials so that like it can store like on the cloud. You can also run without logging in, but that way like you'll be only storing your data locally. Here, like I have already set it up this environment, so like it won't ask me to log in, but like it will say that currently logged in as my username, and then it creates a run for this experiment, which is available here. So when you are initializing this library, like these are the key things that you want to mention. First is the project. So the project is just like imagine like it is just a folder for your experiment, and you give a name to it here, like it's hands-on ML live demo. And then you define the config. So config is where you store your hyperparameters. So these are the variables that you might want to iterate over. So that like you just like give it as a config. So so uh, here like I know like I'll be using learning rate, number of epochs, batch size, these kind of things later as my hyperparameters. So I have listed them here. They don't need to be fixed. Like oftentimes like you experiment and then you realize maybe something else like you want to introduce as a hyperparameter. So like over the life of an ML experiment, like you keep modifying it. So here there are some links that it gives, like it gives you the link of view project at this hands-on ML live demo and view the run here. So if I click here, okay, it's opening the. So it opens up like this, and there is only one run, which is this, like it gives a name fresh rain. There are no metrics logged yet, so nothing appears here. But as we will see, like later, like this thing will starts getting populated as we start writing our data here. So yeah, coming back to our notebook, we can just like it's just our config. I've just printed here. So now like our environment is like we have set it up our environment, and then like comes the data preparation part. So here, as I said, like we'll be using a subset of the CFAR10 dataset. And since we are dealing with images, like typically like there is some form of pre-processing you want to do over 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 images, so that like your neural networks uh, performs in a generalizable way, and that you can define using this like transforms uh, uh, module provided by uh, PyTorch. So here we have composed two transforms to be applied on an image. So first is like it converts it into the tensor. The second, it normalizes your uh, image by this mean and this standard deviation. So and that like like in the next cell we'll see like how do you pass this function. So it just creates a transform function here, and then you can also like optionally pass this target transform function which will map your targets uh, to like from one value to another. So we are using it here. So for example, like as you can see, like it's a very simple function here. It gives you 0 if x equal to 3, other if the input is 3, otherwise it gives 1. So because like we want to map cats to 0 and dogs to 1, and in CFA 10, like cats take the label 3 and dogs take the label 5. So that's why like we have just like made this target transform, which will, because we'll be subsetting our CFA whole CFA 10 data set to just to cats and dogs. So that's why like we have this target transform, which will map it to just 0 and 1. So this is about the transformation functions that you can typically use. Then like you load the data set using this datasets.cfar10. As you can see, like you like can give the transform and target transform functions here. And so let me just run this. So if the data is not already downloaded, it will download it and like cache it in some local directory or like some cache directory. Here I already have the data downloaded, so uh yeah, it just reuse that. So here if you can see like these two statements are just like loading the full data set, and then like I'm identifying which are the indices which correspond to classes 3 and 5. So class 3 is cat, class 5 is dog. And I'm just like doing my training data set now is the subset of the full data set subsetted over the like the 3 and 5 indices. So, and similarly, I'm subsetting the test data set. And then like we create a validation data set. So we choose that, okay, like 80% of the data points from the training set will be using as will be using as training points, and 20% of them will be using as validation dataset. Validation dataset is used to like while you are iterating over your hyperparameters, trying to find um, the 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 best hyperparameter for your experiment. Like you use your validation dataset to validate those choices. So here, like a 80-20 split is a common choice that people typically make. So that's what we are doing. And this command like does a random split of your train data set of sizes, train size and val size. So that will give me my train data set and my validation data set. So here, like it's always a good practice to like kind of like just see your data set and see like if how does it look. So we can try to visualize like some sample images from the data set. As you can see, like they are not very like high fidelity images, but like they do resemble, like some of them are cats, some of them are dogs, and that's what our data set is. So you can also do like more like advanced analysis and try to figure out like how many data points correspond to like a particular class and maybe something else. But here, like I'm just giving you a sample visualization that you may want to do when you're working with your data set that you have created. So after this, like now we have the data set in our space. And then like what you want to create is something called a data loader. A data loader is like another abstraction over your data set, which is it gives you functionality to load data in batches. As I said, like typically in deep learning or machine learning, when we are doing any kind of gradient descent, we are typically doing the stochastic version of the gradient descent or like the mini batch version of it. So like we load our data in batches, and then we like run our model or like our training or evaluation on batches. So this, because like this is such a common operation, so there's like a dedicated functionality given by PyTorch, which lets you wrap around your data set in the data loader object. And here, like some of the key arguments that you want to pass here is you want to pass um, what's your batch size is going to be. So here I'm just using my config.batch size, which I defined when I was defining my WandB environment. So here I'm using the 32 batch size, and sorry, where did it go? Right. And then another key argument that you want to define is like whether you want to shuffle this data set or not every time like you are iterating over your data loader. So for training, you do always kind of want to shuffle your data set. And for validation and test, you want to keep it to false. And that's what we have done. So like we have created this data loaders, train loader, val loader, and test loader. So that concludes our data processing steps that are involved. Are there any questions so far? Yeah. Okay, so let's look into like setting up our model, loss, and optimizer, which are like the key components of our solution. So just give me a sec. Yeah. Okay, so any kind of neural network that you, any kind of model that you define in PyTorch, you you define it as a class which subclasses this nn dot module. Ob nn dot module is just like a easy wrapper that PyTorch provides, which lets you like makes your life quite easy, like in terms of like organizing all the parameters in one place and working through them. So here, like as I said, we have created this class simple binary net, and we have subclassed it from the nn dot module. So any kind of like neural network class that you create, like you want to define two main functions. One is the init and the other one is the forward. Init kind of defines like what are your parameters going to look like what are your model parameters actually are. And then in the forward, like as the name suggests, like you are doing the forward pass of your network. So like it takes your input and it returns um, the output which is expected from your model. So here, like I have like uh, like uh, like I have left it empty, like to implement on the fly, but I do realize that maybe like I'm running out of time, so I'll just uh, just give write the code here directly, and then like we can go over what are the important components of it. So just give me a second. Okay, so this is so here this is like the completed implementation of this neural network. So as you can see in init, we have essentially four parameters. First is W1, which is um, matrix of shape input size cross hidden size. Input size is one of the arguments to this init function, and it is of the shape 3 cross 32 cross 32, which is going to be the shape of our image. And then like we have the hidden size. So hidden size can also be passed as an argument. And remember that like when I was defining my hyperparameters, I had this hidden size was one of the components to it. So I can programmatically pass that hidden size to my network. Uh, So if you look at it, like, so how you want to define a parameter inside your model, like you just create a tensor of that shape. So for example, like here I'm creating this okay. For example, let's for this one, like I'm just want to demonstrate like one. Give you. So here, like if you do torch.randn, like it just gives you like random values of the shape 4x8. So that's what we are doing here. Like we are creating like a random matrix of shape input size cross hidden size. But you will notice that like I'm also sort of normalizing it by some quantity. And in your homework, as well as like maybe if there is some time, like we will see that like this form of normalization, which is kind of like how you're initializing your parameters, is kind important. And but right now, like this is like one way to like appropriately initialize uh, 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 MLP inside your neural network. But there are like other ways proposed in literature as well, which you are going to kind of explore as as one part of your homework. But yeah, right now, like I have just the right implementation here, so everything works. But yeah, and just wanted to point out that like this form of normalization is important when you are initializing a parameter. So so we have this W1, which is like a parameter of shape input size cross hidden size. Then we have the bias parameter for this layer, which is just zeros of shape hidden size. And then we have W2, and which is the your output layer. So this takes this consumes the outputs of the first layer as its input, and then it just gives like one scalar. So that's why it's of the size hidden size cross 1. And even this, like we are initializing it properly, so our neural network works. And then like we can have a bias parameter here. And then like I have just defined my hidden activation function. So I'm with this also, like I'm passing it as an argument. Like if it's sigmoid, I use the f dot sigmoid function. Otherwise, I'm using f dot relu if hidden activation is relu. You can, yeah, just add anything that you want here, like any function. So now let's look at the forward function. So in the forward function, like we get the input x, which is our input tensor of shape batch size cross 3 cross 32 cross 32. So here because like we can maybe okay, like later we'll see one example of a batch. So there like I can show you that the shape is of this, like it's actually, like it's wrong. It should be the 32, comma 32. So it's a four-dimensional tensor of batch size cross 3 cross 32 cross 32. So first we flatten it out, like so this is an operation that can be done, like it's just you're reshaping it. You're keeping the uh, first axis, and then you are flattening out all of the other axes, and this you typically do by denoting it by -1. So all the rest of the axis gets um, concatenated on this second axis. So in this lecture, like I'm not going into like details of all of the operations that PyTorch offers, but the goal is to like kind of give you an overview of how an ML experiment or XML like implementation looks like. So that's why I'm not going too much detail into like how this is like operating under the hood, but yeah, just take the word that like this operation is flattening the image into the shape of batch size, comma, all the other dimensions concatenated, which is going to be 3 times 32 times 32. And then in our forward pass, like if you remember from the like last to last lecture, uh, yeah, last to last lecture that we did on introduction to deep learning, like in the matrix notations, we write it we do the matrix multiplication between X and W1, and then we add the B1. So this will give us a, a tensor which is of shape batch size cross hidden size. And this is our Z1. Then we apply our hidden activation function on Z1 to get our A1. Then we take A1 and do the same operation as Z1, but like this time we multiply it by W2 and we add the bias B2 as well. And this gives us the Z2. And ideally, like maybe we should have done like A2 equal to self dot hidden activation function of Z2. But and then like we should have returned the A2 because like like neurons, all of these neurons also have their non-linearity. But typically, like when like at the output layer, most of the times the non-linearities are kind of hidden inside your loss function. Your loss function already like just like includes the final hidden activation that is going to be used. So, and in this case also it is true. That's why like we are not adding any like the hidden activation after Z2. So like we'll be just returning Z2 here. And that's our forward function. And we have defined this class. We are instantiating it by simple binary net. We give the hidden size, we get the hidden activation. And then this is something interesting which WandB allows us to do. Like we are adding this model uh, like in the WandB.watch function. What it does is, like we'll see later, that like it lets us visualize how our parameters or like the gradients that the parameters it is receiving over time, like that it allows us to visualize that. And we're like there are certain parameters that you can set, like what you want to visualize. So we here like all means that we are visualizing both the gradients and the model parameters. And then there is this log frequency, which is like at like after how many steps we want to visualize it. Because like this is like will kind of store all your parameters and all your gradients. So maybe you don't want to do it after every step. So that's why we define this frequency. We will see those visualizations like when we actually run our network. But yeah, just wanted to mention that that's what this WandB.watch is doing and why is it. And why do we want to do it? Maybe like if there is time, like we can go into when we are debugging this neural network. But yeah, these like just visualizing, like having a visualization of how your parameters are evolving and what kind of gradients they are getting is very helpful when you are debugging a neural network. So any questions so far? Okay. So let's run this cell. Yeah. And then we define our loss function and optimizer. So the loss function that we are using, like typically it's named criterion. I'm not really sure like what's the background behind naming it criterion is, but that's what it is, and that's what I've also used. So we are defining this loss function, like it's already provided to you. Like all of the standard loss functions is already given to you by PyTorch, but like if you want to implement your own loss function, you are free to do that. Like it's this BC with logits loss is just like your binary cross entropy loss, which also has a sigmoid operation prepended to it. So it will take its it takes two, as we'll see, like it takes two arguments. One is your prediction, and the other is your target values, which is your gold label. And then like it applies sigmoid to your predictions, and then like it like applies the binary cross entropy loss function to which takes your y and y hat, which is your goal, target, and predicted values in the function. So that's been already wrapped around for you by the PyTorch library. And similarly, the optimization process, the optimizer is also wrapped around for you in the optim.sgd. So to any optimizer, you want to pass the model dot parameters and the kind of the hyperparameters that this particular optimizer is going to be using. In case of SGD, it is pretty simple. It just takes the learning rate as its argument. So let's just run this. And now maybe let's look at like okay, it's as I said, like when we defined our data set, like it's always good to visualize what our data is looking like. So here as well, like once we have defined our network, like it's always a good idea to visualize like what exactly is that network doing and like how are things looking. So to visualize that, like there is a nice library called Torch Wiz, which lets you visualize kind of the forward pass of a model, your neural network. For that, it needs a sample of your data to operate on. So we'll just get, maybe I didn't run it. We'll get a sample batch from our data loader. And maybe let's also like briefly look like what is our sample batch. So it's actually, let's print its type. It's a list. Uh, the list is of length 2. Let's look at what its first element is. So first element is a tensor. We can see its shape. So as you can see, like it's of the shape 32 cross 3 cross 32 cross 32. So that's your size of your image, and this is your batch size. So, and let's look like what our second element to our batch is. And as you can see, like it's just a tensors of zeros and ones, which is of shape 32. So because like we have 32 batch size. So that's what your data loader outputs. This is a sample batch. And to visualize it, like we will make a prediction on this sample batch. So our model takes the X of my batch, and maybe like I could have also written it like this: X comma Y equal to sample batch. Here I could have, this makes clearer. Then this is my Y. So yeah, let's
We'll need the index 0 for the sample batch.
why do I need I mean I'm running on a batch of
I
examples.
see. Okay.
Yeah, yeah. Because like my forward pass is written for a batch input, so I do need the batch access.
Got it.
Right. So as you can see, like this is what, like it neatly visualizes like what my forward pass looks like. And for this simple network, like it is still like not that complicated, but it can get pretty complicated. Like if you have like very complex networks, but still like it's a good utility to have, and you can, I think there are ways to like neatly organize those complex networks within this library as well. But here we can see that like all of the leaf nodes or the trainable parameters are denoted in this blue box, which is your W1, B1, W2, B2. All of your trainable parameters are here. And then at the end, like we have this loss function, which is getting computed. So you can trace this graph, and like you can verify that it is actually doing what uh, it should be doing. Just a note on this accumulate grad thing, so it's just the implementation detail that like this library actually what it does is like it analyzes the backward pass of your model, and then like it takes that backward pass graph to do this visualization. And in the backward pass, before every parameter, like after every parameter, there is this accumulate grad function, which is um, just a simple function, which is like adding the new gradients that appears to your existing gradients of your model. So I don't think that detail is necessary, but like if you're just wondering like why is this weird thing showing up, in this graph, and that's the reason. So yeah, I mean, we kind of looked at our computational graph and it makes sense. So let's go ahead and let's see, um, uh, like let's set up our training and evaluation loops. So even here, like I thought like I'll go over and write these code, but yeah, I don't really have too much time left. So I'll just go ahead and copy. So just quickly going over our train function. So this is the function which takes our model, our device. So device like PyTorch is a very powerful library, like which lets you use GPUs and TPUs as well, which are the hardware accelerators, which are like specifically designed for uh, like matrix operations. So in this demo, like we are not using it or not even showing what the difference is, but like just for completeness sake, I have this device. It takes the train loader, it takes your optimizer, it takes your loss function and the epoch that you're running for. So this is something important that you wanna like in PyTorch, you wanna call this you want dot train on your model. So this like sets up the right flags inside your model to set it up for training. And then like these are just some variables which we want to keep track of our like the running loss of when we are iterating over when we are doing one epoch of training. And this is just a progress bar object that we are making, which is like just a wrapper around our on our train loader. So coming to the main part, like which is this, the body of our for loop. So we are iterating over our data loader. We are getting the data, the x and the y from and like putting it to the right device, which is which we passed as an argument. And then like one thing that you want to do is like we want to do call optimizer.zeroGrad. So this sets like all of the gradients of your parameters to 0. If you don't set it, like as I said, like as we saw here, there is a accumulate grad operation. It will keep on adding to your the existing gradients that you had for that variable. So we'll keep on aggregating the gradients. So in most of the times we don't want to do that. So that's why like it is sort of important to call this optimizer.zeroGrad before your like your iteration begins. So we call zero grad, and then we get the output. We like do the forward pass, which is simply the model of data. This gives us output. Sorry, the output is going to be this z2 that we kind the return of like our forward pass. And here, like now we are computing the loss, which is like the criterion, like our loss function. It takes our output and it takes the target that we got from our data loader. And this computes the variable, the scalar variable loss. And then we call loss dot backward. So this is what is like main of the core uh, ease of PyTorch, that like it lets you compute all the gradients for your parameters just by calling this loss dot backward. So under the hood, like it is like doing auto diff, which stands for auto differentiation. So it takes your like neural network, like it know, because it has built this graph, it knows like what each intermediate values were like from which functions and from which variables like each of the intermediate functions came from. It applies the chain rule and it can like automatically compute all of the gradients for these parameters. So this is kind of the main line where all the magic is happening, and it is pretty simple and so so much powerful as well. So after you have done this, like you like in all of the leaf parameters that you have, like the boxes in blue, their their gradient gets gets computed and stored in like something like w1.grad or b1.grad. The grad, you can access the gradients by just appending .grad to those variables names, and the gradients gets populated, and then we are doing optimizer.step. So this is what is doing um your it is taking the gradient and it is updating your model parameters by the gradient. So remember, in case of a gradient descent, this operation looks like you have w, and then you take like you take a like a scaled negative step in the direction of your gradient. So like it's going to look like something like w equal to w minus your learning rate times gradient. So that's what like this operation will do. As we'll see later in the class, like these optimizers are not always that simple. Like they these update rules can get complicated. So that's why like it's kind of everything is like abstracted in this optimizer.step. So for any kind of optimizer, you can just call optimizer.step and it will like do its update rule.
Excuse me, is that step function also take learning rate into consideration?
Right, because when you defined your optimizer,
Oh,
you
I
did
see.
give
Okay.
the learning rate here. So it knows the learning rate. Yeah, so there were two things that you gave. You gave the model dot parameters, which is a list of these blue boxes, and you gave your learning rate, which is the uh, your hyperparameter for this particular object, your optimizer object. So it does take the learning rate into account.
Thank you.
Okay, so that kind of concludes like the crux of your training loop. And here, like it's just some logging statements, like we are updating the running loss. We are then like appending it to our progress bar, and also like we are logging it at to the our WandB object. We'll see that like these variables like will come as nice graphs when we like actually run this training loop. So that concludes our training loop. And then we come to the evaluate. And yeah, in the interest of time, like I'm not going too much detail on the evaluate loop, but like you can go over this code, and like it's not really not that complicated. Like it the essential bit is this, that it is like getting the data, it is doing the forward pass, it is computing the test loss by um running the loss function, and then like we are also measuring the accuracy, which is we make the prediction as like if the sigmoid of my output was greater than 0.5, then I say it is 1, and then I check whether like this is equal to my target or not, and summing it up over my batch axis. Also, like here, when you're evaluating, it's always like on like in machine learning, it is like these things are very fragile. So it is always better to have some grip over like what is happening at different stages of your experiment. So if so, as I said like earlier as well, like in every step, like it is a very good idea to like have some visualizations which gives you insights into what's happening. So here as well, like we are kind of saving the first batch of sample predictions, and then like we are adding that to our WandB logs. um, and we will see that like even these images and their predictions will come nicely when we open our dashboard. So that's our evaluation loop. And then we come to the training model. Here it's a simple loop, like we are iterating over like our number of epochs that we defined in config. We are training the model, we are evaluating the model on validation split, and we are also evaluating the model on the training split to get the training accuracy. So this way, like we can sort of monitor whether like the model is, or like if the training accuracy is increasing, but the validation accuracy is not increasing, that means the model is going more into the regime of overfitting the data. So that's why like it's yeah, a good idea to always keep track on the your training accuracies or training, the difference between your training accuracy and your validation accuracy as well. So, okay, let's finally run this training loop and see what do we get like in. Right. So this model is running. I think I'm currently running for 10 epochs. And here like after every epoch, I'm printing the average, on the validation set, average loss and accuracy, and on the training set, average loss and accuracy. As you see, the training accuracy is always a bit higher than validation set. And when this difference becomes larger and larger, when the training continues, so the like now we can see the magic of the weights and biases library. Like if I reload this page, because I was tracking everything, I do see like these nice visualizations. This is my validation loss over the course of training, which is a bit jagged. um, this is my training loss, like after every step. That's why like it is so wiggly. But so typically like you kind of smooth out your training losses. uh, Here you can do it by like, yeah, so if you smooth out, you can get the overall sense of what exactly is the trend. And then as you can see, the training accuracy is monotonically increasing like as we continue doing training, but the validation accuracy, like it is more wiggly, which sort of makes sense because like we are training on like our training data, and validation is something like which is just for testing. But if you are like, if your model is generalizing, then like even this should like have the same trend as your training accuracy. Now come to the other important things that we logged. One was gradients. So here, as you can see, like these W2, W1, B1, B2 parameters, like you can see the gradients of your of these parameters. So like it shows like for after every 100 steps, like we are logging it. So like it kind of gives you a distribution of what these values look like. So in our case, like it kind of remains consistent, which is sort of a good thing. Like you don't want to get like very high or low gradients. Like you want to get something in which is like maybe centered around zero, and like is sort of maybe evenly distributed on the positive and negative side, and is not too large. And that's what we are seeing here, which is like a good sign. And then we can also see our parameters, like so like similar to the gradients, like we can like it is giving you a distribution over like your parameter values. So this is also like sort of something which is consistent, centered around zero, which makes sense. um, then like there is this panel which is media. Since we after every iteration, we were like when we were evaluating, we were taking the first batch, and we were uh, like visualizing like how what is my prediction, what is the goal target. So here, as you can see, maybe initially the model wasn't that good. For this example, like it is predicting cat while the goal label is dog. So it is sort of making some mistakes. So I'm not going into like into in-depth analysis, but like this is, you can see that like how this can be valuable like over the course of training. Like you can see like maybe where you are making mistakes and what kind of mistakes you're making. So this is forms of visualizations are pretty helpful, which these libraries enable you to do. So let's come back to our code. So here, like our training loop is done. At the end, like at the end of like your experimental loop, like you want to test your model on your test set, and this like is similar to like what we did earlier in the training loop, that we were calling this evaluate function, but this time we'll give the test loader and just name it as test. So it will give you the test accuracy, and as you can see, like it's 65.5 in our case. And after once you're finished with your experiment, you want to call like wandb.finish. So it finishes this run, it marks as at finished, and it gives you this nice summary of your run history. So, and sorry, these variables will, like now if you reload, then like you can see this test loss appears, this test accuracy appears, and in the media section, these test sample predictions also appear. So that's mostly completes like one run of your ML experiment. But like as I said earlier, like in a typical life cycle of an ML experiment, like you want to keep on iterating over it. You want to like find the basic thing at least you want to do is like you want to see like the hyperparameter choices that you made, like uh, what are the right things to do. So these libraries also allow you to do a hyperparameter sweep, which is like it allows you to automatically explore different configurations to optimize your model performance. And in the interest of time, I'll be quickly going over it. But of course, like you'll have access to this notebook, and so you can explore and in your time like how to do this. But like just going quickly over it, like it starts with you defining a sweep configuration. This is like the method of your hyperparameter sweep that you want to do. You can like typically like you can do like a you can set it to base, like that's like a good default choice, which will like do a informed hyperparameter space exploration if you are limited on compute. But if you want to be exhaustive, you can do grid, which will uh, like explore all of the hyperparameter like cross hyperparameter choices that you could have made. But here like we'll just do base, and then you want to define this, like what metric are you looking for, like what is your what like because like here like I want to maximize my validation accuracy. So like my metric's name is validation accuracy, and my goal is to maximize it. uh, then like the parameters of your like what hyperparameters you want to um, do your hyperparameter exploration over. So here I'm just giving a set of values for learning rate. I want to do hyperparameter sweep over like 0.001, 0.0001, You can add anything similarly for batch size, hidden size. These are the key things that I want to ablate over. And I'm keeping the number of epochs to be something small because like for hyperparameter sweeps, you don't want to do full training. You want to like just quickly test whether like this, how like is this hyperparameter good or not. Um, so like it is generally a good idea to keep it small. And then you give the sweep configuration to wandb.sweep. You specify which project you are doing. So I'm just repeating that name that we gave earlier. This will give you a sweep ID, which is this. Everything will get logged here. Like it gives you the URL. And then here you define the sweep train function, which will take like one particular config, and the config will be decided based on some some instantiation of the all of the choices of your hyperparameters that exist. And then you are running your training loop here, and then logging all the important metrics that you want to log. And it should have this val accuracy as a as something to be logged, because like that is what we are trying to optimize in our hyperparameter sweep. So this is something very similar to what we did earlier. So I just define the sweep train function, and then you run your hyperparameter sweep by this command, which is um, and as you can see, like it is kind of like sampling one configuration of your hyperparameters. Like among this, since we are using the base method, like it is doing some informed choice over these hyperparameter space. And it is like running it for 3 epochs. It is giving you its run history, and then it does it iteratively, and everything gets logged here. So far, like 3 runs have completed. Maybe just let's wait a minute. I think it shouldn't take too much time. In the meantime, if there are any questions so far which I can quickly answer, I would be happy to take them. It should be close to being done on the 8th experiment. So this one I'm just running for like 10 total experiments like this. I specified here. Okay, I didn't specify, but okay. Let's look at the intermediate. So like these are all the different runs that we did, but this is too confusing to see. So like it also lets you kind of visualize this in this neat framework that like what is the best accuracy that you got, and it was this run. You can open this run, and then something also important is like it also gives you this visualization, like depending on all of the runs it did so far, like what it thinks like is the important, like it computes the correlation factor with of that hyperparameter with the final metric that you were optimizing for, and like is it correlated or not. Based on that, like it gives you like an importance score. And here so far it says like hidden size is sort of the more important thing, and then comes the learning rate. Batch size is sort of not important at all, which is sort of true in most ML cases. But and this is also something good that it lets you visualize it. It gives you like these individual runs with different paths they took on the different axes. So if here, as you see, like this is the best curve, and like this, and this was with learning rate 0.01, with hidden size 256, with batch size 128, and that gave you the best result. Maybe I should reload it so that like more runs are populated here. Yeah, as you see, like right now, I think because like I didn't give a count of how many experiments to do, it is running all of the possible experiments. So, but I mean, this is pretty neat. Like it lets you visualize like what hyperparameters are important for you and what is their effect in the final accuracy that you are getting. So, and like in a typical lifetime of an ML experiment, like you are like doing these iterations again and again, and this is a nice wrapper to do it. And now if you see, like it says like learning rate is the most important factor, like once more runs got populated. So yeah, that's mostly it. um in the notebook, like I do have like a couple of things about like what like some standard practices to do, like if you want to debug your neural network, because oftentimes, like as I said, like these are very like brittle in nature. Even like something very small, like something like initialization can break them. So you do want to debug them. So like there are like some general rule of thumb kind of, or like some litmus test that you can do to kind of debug your neural network. I'm not going in this lecture, but this notebook will be available. So yeah, you can take a look at your own time.
Okay, well, thank you, Nilesh. That was, I think, very helpful for people who will be doing homework too, and also I think further on in the course.